So what we're going to do now is, first of all, I want to be able to get an empirical distribution pictured for these truncated and censored data, right? And I do know that if I have a data set available, and if the data set is complete, right, then in principle, if you look back at the web lecture from last week, then you can visualize this data set with a tool like the empirical CDF or something, right? And now we want to adjust this empirical CDF so that it is capable of taking also the truncation and the censoring into account. And the first thing we need is a certain notation to represent our data, right? And we're going to work with data which are possibly left truncated, right censored. So what we're going to do is, for each individual data point, we're going to list the truncation point for that particular observation J. We're going to denote it with DJ. So DJ is 0 if there is no left truncation subject to our observation J. Then we're going to use XJ if we have the observation which is not censored, and we're going to denote with UJ being the observation in case there is right censoring. Okay, so the scenarios are, for every observation, you're going to record the lower truncation point with DJ. In case there is no particular lower truncation, then you just put the DJ equal to 0. And then for each loss, you're either going to record the XJ if the loss is fully observed, so if it's not subject to censoring, or you're going to denote it with UJ in case it is right censored. And in that case, you know that the ultimate loss is going to be beyond the UJ, but you don't know how much it will be in reality, right? So if we then go back to the notation that I introduced on the iPad, so here we have our unique values in the sample, the Y1 up to the YK. We're going to denote SJ, the number of times the uncensored observation appears in the sample. And we're going to denote with RJ the risk set that comes with the ordered observation YJ. Then first of all, now we need to think about how would that risk set be defined in case you have the left truncation and the right censoring. And so that's the reasoning we're going to build up here. And that's the expression I want you to think about a little bit. So if we look at the risk set RJ, then in principle, what we're doing is we're counting the number of observations which are larger than or equal to the observed unique outcome Yj. And so what that now becomes, in case we're dealing with right censoring left truncation, is that we're going to count how many XIs did we observe, so full observations, which are above this Yj or equal to the Yj. How many of the right censored observations did we observe, which are above or equal to the Yj? And what we're going to subtract is the number of DIs, left truncation points, which are above or equal to the Yj. And why do we subtract this last part? That is, of course, because if you look at left truncation, and if you have a DI, a left truncation point that is larger than or equal to Yj, yeah, then the observation that comes with this left truncation point DI, it cannot be part of the risk set Rj, because that observation will always, if it is in the sample, it will take a value larger than the left truncation point, right? So the first two terms, they add how many of the fully observed losses, of the right censored losses, are larger than or equal to the Yj value. And we need to subtract how many truncation points do we have above or equal to this Yj, just to make sure that when we're counting the risk set, yeah, that we make sure that the observations that we count in this risk set, that they are actually observed, so that they are not subject to left truncation. Yeah, you can also put it the other way around. So then you're going to start with how many of the DIs are strictly smaller than Yj, how many of the and you subtract how many of the xi's are strictly smaller than yj and how many of the ui's are strictly smaller than yj. And do remember what you want to count in this risk set. You want to count all the observations in your sample, which will observe the outcome of interest at a value that is larger than or equal to the yj for which you are counting this risk set. Okay. Now, that's what I try to, what I just explained, that's what I try to summarize here on the sheet. So if you look at the definition of the risk set, and I give you a definition which is more from a survival context. So in a survival context, we're typically interested in time to a certain event or age at which a certain event will happen, right? But you can keep this kind of problem or application in mind for now, but do know that this notion of the risk set is of course transferable to the setting where you would, for example, look at the ultimate loss that comes with an insured event, and where you are looking for a distribution of this ultimate loss in case you're working with a sample that is subject to left truncation, right censoring. Yeah, so these notions can be transferred. But if we think about the survival context intuition, then we're going to say, yeah, what is the definition of the risk set Rj? Well, the risk set contains all the individuals who are still under observation at time or at age, or however you want to call it, yj, at value yj, right? Because with survival analysis, you're following observations over time. So the risk set Rj will consist of all those individuals who will observe the event of interest at or after yj, right? So that means that who are you going to include? You're going to include all who observe the event of interest at age yj, at time yj or later. You're going to include all those who are censored at value yj or later. And you're going to not include, so you're going to exclude those who are not yet in the group at age or time yj. That means those who you will only first observe at that particular age or later. Yeah? So with the three bullets, with the plus sign, with a minus sign here, you recognize the specification that we gave for this risk set on the previous sheet. Yeah? So that's the idea. And it's the idea put down or explained intuitively here if you have the survival context in mind. But what works for the survival context also works for the context where you look, for instance, at the ultimate loss of a claim. Yeah. So the key point here is the risk set is the number of people observed alive at age or time yj. If we transfer that phrase to the context of loss modeling with claim sizes, you would say the risk set is the number of losses that you observe at a certain value, at a certain size yj, let's say. Yj or larger. Yeah. So what we want to do now is come up with a tool, and that's the famous Kaplan-Meier estimator. So we want to come up with a tool to produce an estimator of the survival function in case we have these censored and or truncated data, right? And so the whole idea is that we have to be careful. We cannot just use the empirical CDF in case our data are subject to truncation and censoring. We need to come up with an adjusted empirical distribution, right? So let us first explain how that would work. Kaplan-Meier product limit estimator. If you follow this link, you can get a bit of more background. And the reasoning goes as follows. So if you look at the Kaplan-Meier estimator of the survival function, you're going to start with the survival function in 0 equal to 1, right? So we're going to assume that we work with distributions which have all their support on the positive real line. So we're going to let it start our survival function in 0. We're going to let it start from 1. Now, because we didn't, because the first observation, the first actual observation that we're going to see is denoted with y1. right? So the y's that were the unique values of the event of interest that we observe. So the first outcome that we see is the y1. So that means that our survival function is going to stay at 1 until we arrive at the point y1, right? And just before this point y1, we had the risk set, R1, of people or claims or individuals who were at risk of seeing the event of interest, and as one of them actually observed the event of interest. That's how we defined S1. Huh? That's the number of times we observed the unique outcome Y1. And for R1, we know that's the number of people, that's the size of the group who was at risk of seeing the event of interest at the value Y1, right? Or larger. So the probability of going past Y1 would then mean, yeah, S1 out of the R1 observed the event of interest at Y1. So the complement of that, so 1 minus S1 divided by R1, that's the probability of going beyond the value Y1. So that should be the value of the survival function in Y1, because the survival function in Y1, it's the probability that the random variable of interest is strictly larger than the Y1. And then we move on. The survival function will stay at that value as Y1 until the next outcome, the next unique outcome that we observe, that's the Y2. Now the new survival value at Y2, we're going to denote that with the following product. And that's where the name is coming from, at the product limit estimator. And in order to make sense of that, we need to think conditionally, right? And I'm going to explain that on the next sheet. So I need to think conditionally. And if I look at, say, t, the random variable of interest, then I know the probability that t is strictly larger than y1. That's 1 minus the number of people, or the size of the group, who experience the event of interest at y1, s1, divided by the size of the group who could potentially observe the event of interest at y1, right? And if I then move on, what I next want to know is, yeah, what would then be the conditional survival probability, the probability that t is strictly larger than y2, given that t is strictly larger than y1. So if I do the same kind of reasoning, then I'm going to say, well, right before y2, I've got a group of size r2 who is at risk of seeing the event of interest at y2. And s2 out of this group actually observed the event of interest at y2, right? So the probability that t goes beyond y2, given that t already went beyond y1, is 1 minus this s2 divided by r2. But this conditional probability, that's not what my survival function is picturing. What my survival function should picture at y2 is the survival probability at y2, right? So what I'm going to do is I'm going to say, well, that survival probability, I can write it in conditional thinking as a product of survival probabilities. And those who are in the life insurance mathematics course, they know how that goes. The k-year survival probability is a product of 1 year survival probabilities. It's the same kind of conditional thinking that you see happening over here. So if you use the law or the expressions for conditional probabilities, then you'll see that if you work out this conditional probability, then you'll get the probability that t is strictly larger than y2 divided by the probability that t is strictly larger than y1. That probability cancels out in the numerator and the denominator. So we're left here with the probability unconditionally that t is strictly larger than y2. And we can see that as a product of these conditional survival probabilities. And we can build up this reasoning. Huh? So the next step would be, what is the probability that t is strictly larger than y3? We can write it again with a conditional thinking and get our expressions as a product of 1 year survival probabilities over here. So this is why we call the Kaplan-Meier a product limit estimator. And it also is an estimator that takes the truncation and the censoring into account, because we work with these risk sets and we work with these S's, the number of times we saw the event of interest. And with the risk set, how we take care of the observations that we didn't see because of truncation, or the observations that we don't see in full because of the right censoring. Okay, so in the end, I'll get an expression like this. So here, that's just a mathematical way of writing down all these products. So you could take a look at that. The only thing that is perhaps a little bit strange here is, what is the survival function evaluated in t if t goes beyond the last observed y value? So if t is larger than or equal to the yk. Well, there you could say, I'll just leave it at the last value that I calculated, or I really put my survival function at 0, because the survival function goes from 1 to 0, we know that. So that's a choice that you need to think about. In case everybody in the sample has died by a certain value. Empirically, you could say that surviving past that age is not possible, so you could put it at 0. But you could also say that because of censoring, it's possible that the age of the last death, that there were still some people alive, but all were censored prior to death. So in that case, you could keep the survival function at its last calculated value. So it depends a little bit. If really everybody in the sample had died, you could really put it to 0. If you say, okay, I didn't see the death of all my patients or all my individuals in the study because some were censored, then you could just leave it at the value calculated over here. I also denote it with Sn. So the n, that's my notation for an empirical estimator. It's similar to the empirical CDF, but here it's for S, the empirical survival function. Yeah. So let's do that now before the break for the dataset D2, right? So for the dataset D2, we had the following pieces of information. So we restructured the information a little bit. We refer to the left truncation point, the D. We refer to, is it an actual observation or is it a right censored observation? If it's an actual observation, you'll put it at xi. If it's a right censored observation, you'll put the value at ui. So whenever you will have an actual observation, in this particular example that is underneath this particular data set, it means that you would have observed the death of this policyholder at this specific time xi, right? If the policyholder canceled, surrendered the contract, or if the policyholder went up to the policy expiration, then you would not see the actual event of interest, but you would only see the right censored value, right? Also, do note that for the last 10 observations, I've got a D that is different from 0. So there we saw people only entering later. We were not following them from time 0 on. And of course, once I have the information in this display, it's just a matter of calculating the R's, calculating the S's, calculating the unique Y's. And you see that pictured over here. So perhaps for these unique Y's, let's go back. Here we see which values for the actual event of interest we registered. It's a 0.8, it's a 2.9, it's a 4.0, a 4.1, we've got a 3.1, that kind of value. So these are listed over here. In the second or third column, I should say, we're just going to count how many of these events actually took this particular value for this outcome of interest. And then here in the last column, you're going to denote the risk set. So let's do one. R1 would be the risk set that corresponds to outcome 0.8. So we're going to include all the observations for which X or U is larger than or equal to 0.8. And we're going to subtract the observations for which the D is strictly smaller than 0.8. Yeah? Smaller than or equal to, I should say. So what do you see here? If you look at the D's, there are, if you look at the D's, we have, for the first outcome of 0. So the risk set is a number of observations that will see the event of interest at a value of y1 at least, and y1, the first unique value that we observe in the data set of the outcome of interest here is 0.8, right? So if we calculate the risk set, we can do it in different ways. So as Milou explained in the chat, what we're going to do in the first type of calculation is we're going to look at the number of the DIs, which are less, now I have to be a bit careful with the signs. So we can look at the number of the DIs, which are strictly smaller than 0.8, right? And if you look at the data set, then you see that this is the case for 32 out of the 40 observations, right? So for 32 of my observations, I'm following the, in this case, the policies or the policy holders. I'm following them from a point on that is strictly smaller than 0.8. And then what I'm going to subtract, so I've got these 32 policies which I'm following, but then I see that if I look at the XIs, because I'm looking at the first outcome that I observe, so none of the XIs is strictly smaller than 0.8. So what I have for now is 32 minus 0, but I do observe that 2 of the censored values, so 2 of the U's, are strictly smaller than 0.8. So what I've got in total is 32 minus 0 minus 2. So that's 30 individuals who are at risk of seeing the event of interest at the value of 0.8. Yeah. So you can reason like that. It takes me also a bit of time to get the explanation correctly. So, but that's the explanation that Milou gave, and then Louis asked for the alternative specification. So the way how I would do that is I would count the number of XIs and the number of UIs, which are larger than or equal to 0.8, right? And if I look at the combination of the XIs and the UIs, then you see that there are only 2 policies here, which gets, in this case, a censored value that is smaller than 0.8. So if you look at all the XIs and the UIs, which are at least as large as 0.8, then you have 38 of them in total, right? And then you're going to subtract those DIs, which are larger than or equal to 0.8, because those observations were not yet in the study at 0.8. And it means if you look at the guys from 33 to 40, so these are 8 in total, those are not yet in the study at 0.8. So they cannot observe the event of interest at the value of 0.8. So the second reasoning is this 38 minus 8, which is also equal to 30. And then you can move on like this with putting the risk sets together and putting the unique values together, etc., etc. And once you have these columns, so the unique Y's, the S's, and the RJs, then it's a matter of plugging in and the conditional thinking, the product limit estimator, to reach the Kaplan-Meier estimator for this given data set D2. So this is a picture of my survival function of the event of interest that does take into account in the appropriate way the censoring and the truncation that is present in the data set. Of course, if there is no censoring or truncation, then you could just move on with your empirical CDF, your empirical survival function. But if there is truncation and if there is censoring, so if you're working with modified incomplete data, then you should picture them in the correct way. Now, what are we going to do in the next classes when we switch to R, which is eventually our goal? So if I do this in R, and don't forget about the coding right now, but what you will get would be something like this. So you see in this case, for quite a crude data set, you get the empirical survival function, you get confidence intervals that come with it. We didn't discuss the confidence intervals, but do know that that exists. So you get something like this. Now, what could I do with that? If I'm actually then fitting a model to this data set, then one way to use this Kaplan-Meier is to picture the survival function that comes out of my parametric model, which I calibrated on my data, right? To compare this fitted parametric model with the empirical data as pictured by the Kaplan-Meier. So that's something that we're going to do later on when we're fitting severity distributions to loss data subject to truncation and to censoring. One of the things we can do is we can picture the Kaplan-Meier, that's our reference line, so to say, and then we can put the survival function of the parametric model that we propose for the data. We can put that on top of the Kaplan-Meier to see whether our fitted model makes sense for the given data. And in fact, we already had a picture like that, if you remember, when we were talking about the mixtures of Erlangs. If you go back to these lecture sheets, there I had this kind of visual, where I had the Kaplan-Meier, didn't call it the Kaplan-Meier at that time, but we had the Kaplan-Meier there. We put the fitted mixture of Erlang survival function on top, and we could see that the mixture of Erlang fitted distribution was then close to the empirical data, right? So that's one way how you can use this tool, this empirical survival function, to as a sort of benchmark or baseline if you want to investigate the goodness of fit of your proposed parametric model for data subject to censoring and to truncation. Yeah, so that hopefully will become clear when we do some R sessions in the rest of December.